Okay, so good evening. We represent the Rover #1 team, and we will proceed to expose the idea that we developed during the hackathon that correspond to science and engineering mission. The Rover #1 team, #1 team is conformed by multidisciplinary part fields. We convinced that if we could have more detailed information for the rover and how communicate with other subsystems, it will possible to, well, for us, design, program, and build what we are proposing. The rover drill and extraction method.
The proposal consists on a special model for the geophysical and extraction methods for the rover mission. When we started with the idea to explore the extraction method, our main objective was an analogous mission that has the objective of finding out areas that are possible for collecting mineral or water samples, as well as explore tools and methods to be used in rover missions, helping to avoid the astronauts' exposure and obtain maximum value per pound to return Earth.
From now on, we'll focus on trying to answer the question of where to do the digging. In the following diagram, we show how to propose the mission is distributed between the extraction with experimental block and the engineering block, which are often connected to the data analysis and processing. In the following slide, we will talk about it.
This diagram shows our proposed concept of operations. First, we suggest we start with the identification phase, where we will look into the potential area to be studied and we will characterize the expected soil properties. Once an area is defined, we will move on to our first exploration phase. With radar technology, we will find the soil composition of the first layers of the lunar subsurface in order to develop a drilling plan for the next exploration phase, the resistivity method. On this third phase, we will use the drill to bury a set of electrodes into the ground, and then we will use them to create an underground electric field. Finally, the data collected from measuring this electric field will give us enough information to create a 3D map of the lunar subsurface. Now, we will go on to explaining more about the lunar soil composition, the drilling system, and the geophysical method.
Lunar mineralogy is conformed by three principal minerals: olivine, pyroxene, and plagioclase feldspar. Also, we can divide regolith into types: dry regolith and frozen regolith. The dry regolith has irregular particles that change important properties that make it a special soil never seen on Earth. On the other hand, frozen regolith just contains iced water presented in craters mainly. It is important to know some regolith properties so we can drill the soil. In this table, we describe different minerals where the highest hardness is 8 Mohs. So we need to drill that overpass that limit. Also, we have different densities. Okay. It is important to know some regolith properties so we can, okay, thank you. On the, yes, the second one. No, the other one, the second, earlier. Okay, we also have different densities by depth, showing 1.71 grams per cubic meter at 60 centimeters and increasing. Finally, knowing some geophysical characteristics, we can detect minerals by their chemical components like iron or silicon. Next. Among the electrical properties that can be found in the lunar regolith to accomplish the proposed experiments are dielectric permittivity, electrical conductivity, magnetic permeability, and if the terrain maintains a balance in these three variables, locating the samples will be as simple as the method shown. Next.
After obtaining the analysis of the lunar surface, the time has come to start the rover, optimizing and abilities to the maximum. According to the chemical properties of the materials, we have analyzed different options. The best result for use one to make a tool change for each type of property. choose considerably, avoiding tool wear and making the most of its potential, having a tool chains for the correct extraction of the material. We opted for the best drilling system and great depths, adapting and demeaning machinery type extension to achieve depths of up to the 50 meters.
After scanning with the radar method and probing the promising area, the rover will select the first tool of drilling. Proceed with deploying the couplings to avoid movements and vibrations. Then start drilling the surface. Being the case, you can make a tool change if needed, then collect the debris of storage and finish drilling.
Now we go on to the geophysical methods, which are used for non-destructive analysis of underground layers. They work with fundamental physics principles and have been used in geological studies for decades. For this project, we propose the use of two of them, the ground-penetrating radar and the resistivity method. How the ground-penetrating radar works? It is a method that consists in the emission of electromagnetic waves through the ground in order to measure their travel time. This time might change depending on the underground layers that the wave encounters, letting one part of it to be refracted deep underground and the other to be reflected back to the surface. Why should we use it? This is a proven technology. It's currently being used in the Mars rover Perseverance, the Lunar Reconnaissance Orbiter, and the Chandrayaan-1. Also, it has adjustable depth. We can measure from 5 centimeters up to 30 meters through our frequency modulation. And finally, we will be able to identify underground objects that might interfere with the drilling process for the resistivity method.
The resistivity method consists of introducing current onto the ground employing electrodes, and then measuring the voltage in the other electrodes. The relationship between both magnitudes, the one that we injected and the measured one, give us a resistivity. In that way, it is possible to know what's on the subsurface, where it is, how deep it is, and how extensive it is. The collected data is then converted to resistivity values, which conform to a vertical electrical sounding. Then these values can be processed by the echo of the rover. In order to the engineering and science mission be affordable to the analog missions, we base the implementation on one instrument that can be easily constructed from simple components that are available in a store that sells electrical parts. So we present now the cost report. The components we need to implement the resistivity method are batteries, wire and alligator clips, 2 digital multimeters, and at least 4 electrodes. As you can see, there are some recommended links where you can buy the components. These are the materials and the cost for the radar method. And in this and the following slide, you can see as well the components and materials, but now for the drill.
Now, we'll do a quick overview of the proposed activities necessary to implement the project into the Asclepios mission. For example, we're currently showing the 4 main tasks for the first phase of the project, the identification of the study area. The next phases are divided into 2, technology development and mission duties. Here we are showing the proposed timeline for the development of the radar module from conceptualization to prototype and final integration. These are the 4 main duties of the radar that will be performed on the mission. If you want to take a deeper look into the proposed plan, you can click on the link below that we will share later.
It was possible to develop a concept of operation for moon mission that can be implemented in similar analog missions, apply a geophysical methods and drying system adapted to the soil moon condition that make it possible to transport records and samples, preventing humans and risk their health without moon dust. In addition to delimit the search area, it is sufficient to collect samples and analyze it next, and in order obtain abundant resources to production. We want to continue with the idea in the following months, and well, following the list of activity, that we proposed in the documents. I think that is all, and it's time to question and answer.
Okay, great job. I really like your slides. At this time, we will open up the floor to the mentors and the jury for questions. I would like to start with the first question. Can you go back and show your final budget slide, please? The next one. Next one. So your total budget is $34,000 US, or is this an error?
Is just for this area. We divide all the project in models. So it's the full price, but it's just
They are suggested materials. Although we put the more cost, the one that costs more, but in the report that we sent to you, we present more low cost solutions. This is what this is only the highest one for the drill, only for the drill.
Okay, I will take a look at the final report. Okay, do any other of the mentors or jury members have any questions before we move over to the participants for questions?
Yes, actually I have a question. Congratulations on your presentation. It was very clear, and I think we got all the experiments that you'd like to perform. So you've mentioned a lot of different Mars missions with rovers, and the fact that the things you're proposing to test have already been tested. So how would you, to what extent would you qualify your idea novel?
Yes. These missions, especially the Lunar Reconnaissance Orbiter and the Chandrayaan-1, they have a problem. They only work on flat, smooth surfaces of the bigger craters on the moon. What we're proposing is that we can tackle all the areas that this technology can reach. So we can go into maybe more uneven terrain to do a more in-depth look into these areas that for the moment are actually obscure to these technologies.
Okay, thank you.
Does anybody else has questions? No? Then I guess we're gonna start again in 6 minutes, if I'm not mistaken. Thank you very much for your presentation.
Thank you.
Thank you.